Hello students, in this class we are going to revise some of the important topics. First we are going to start with the chapter number 1, electric charges and field. So important derivations we are going to derive. In the later class we are going to discuss the 3 marks theory type questions as well as 2 mark questions. And then we can discuss some multiple choice, the MCQ questions. So first question, so derive an expression for electric field due to an electric dipole along its axis. So this derivation we are going to derive. So before that we should know what is the meaning of electric dipole. First we learn that one, then we derive the derivation. So what is electric dipole? A pair of equal and opposite charges separated by a small distance. Okay. Take the question. Derive an expression or obtain an expression. Expression for electric field. There is an electric field due to electric dipole along its axis. It's also called as what? Dipole axis or axial line. So all meanings are same. Okay. Many times this question repeated in the annual exams. Okay. So derive an expression for electric field due to electric dipole along its axis or dipole axis or axial line. Okay. So first we'll learn what is electric dipole. A pair of equal and opposite charges separated by a small distance. So I'll take one charge here and one more charge here. So one positive charge I'll take, another one is negative charge. This is plus q and here is minus q. These two are separated by a small distance. That distance will take it as how much? 2a. Okay, that distance I'll take it as how much? 2a. So this distance here to here is 2a. This is 2a from here to here. Mention it properly, 2a. This is 2a. Okay, now this line, a line passing the charges, this is called as, this is actually dipole. A pair of equal and opposite charges separated by a small distance, that is called electric dipole. A pair of equal and opposite charges separated by a small distance, that is called electric dipole. A line passing through the charges. Now this line or this axis is known as axial line. Okay. So we have to calculate electric field due to dipole along its axial line. So I'll take one point here, P. Let P be a point at a distance R from the dipole. Now from where I have to take the distance R? We have to take the R from where? From its midpoint, somewhere here. That distance is R. From point P to its midpoint somewhere here comes. Actually center of charge. Okay. So what is the distance from positive charge the point P? That distance actually becomes R minus A. Correct? R minus A. Why R minus A? Because this distance is A, here to here, and here to here is A. Because total distance is already mentioned 2A. From plus Q to minus Q it is 2A. From midpoint to positive charge is A. Similarly, midpoint to negative charge is A. So this distance becomes R minus A. And from point to P to this negative charge that becomes R plus Ca. Okay, so I hope this much clear here. So just elaborating this one. So you can cut short and you can draw this one. If you draw this like this, better. This is R plus C. Okay. And after that, what other things we should know? We should know these things. One is dipole moment. So the required things, I'll write the formulas here. Dipole moment formula is P vector equal to 2aq p cap. This is called dipole moment. And direction of the dipole moment from where to where? Minus q to plus q. And SI unit of dipole moment is coulomb meter. SI unit of dipole moment is coulomb meter. Okay, just ignore this line. So coulomb meter. SI unit of dipole moment is coulomb meter. And what is the electric field due to positive charge? Positive charge electric field is outward. Negative charge electric field is inward. Positive charge electric field is outward. Negative charge electric field is inward. So these are the basic information we should know first before deriving this one. Okay. So I'll start my derivation now. So I'm going to apply electric field due to multiple charge concept. So I'll write here now first electric field at point P due to plus Q is electric field at point P due to plus Q is. So electric field, write the equation first. You can write the equation. So what is the formula for electric field? 1 by 4 pi epsilon naught Q by R square is the formula. We'll write here now. Electric field at point P due to plus Q is. So what is the formula? E plus Q equal to, I write the formula E plus Q, that is vector formula, right? That is equal to 1 by 4 pi epsilon naught charge Q divided by distance. What is the distance? R minus A whole square into P cap. Okay, why like this into P cap? Now, what is the electric field due to the positive charge? Electric field due to positive charge is outward, and we want electric field at point P. Therefore, due to this positive charge will become like this, from positive charge towards the point. And also we know the direction of the dipole moment. Direction of dipole moment from where to where? Minus Q to plus Q. Starting only I told that direction of dipole moment is from minus Q to plus Q. Now this direction and this direction both are same. This and this both are same. If I written here P cap, meaning direction of the electric field and dipole moment both are same. Okay. So next I'll write here electric field at P, same point. So electric field at point P due to minus Q is. So the formula I will write E minus Q equal to 1 by 4 pi epsilon naught. Charge is negative, but no need to substitute the minus sign, only you write magnitude. And what is the distance here from negative charge to the point P? The distance here is how much? R plus A. So I'll write here now R plus A whole square. Okay, now what is the direction of electric field due to negative charge? Electric field due to negative charge is towards the charge, inward, that is towards us. This is the direction of electric field due to negative charge, towards. Now this direction of the electric field, E minus Q vector and P cap, both are in the opposite. Check the arrow mark. This arrow mark and this arrow mark both are opposite. Opposite means vector we write as what? Minus P cap. We write a minus, but your name is P cap. So become minus P cap. Where minus indicates electric field and dipole moment both are in the opposite direction. Therefore, you calculate next step then resultant electric field. So what is the resultant electric field? That is E vector equal to E plus Q vector plus E minus Q vector. It's a vector form. Resultant vector, total electric field. Now what you have to add both the equations. So I'm going to get resultant. E plus Q is here. 1 by 4 pi epsilon naught q divided by r minus a whole square into p cap minus 1 by 4 pi epsilon naught q divided by r plus a whole square p cap. Now think why minus sign? Because this minus sign shifted this side. This minus sign wrote this side. Okay, next. So E vector is equal to Q is common, take outside. 4 pi epsilon naught common, take it outside. So become 1 divided by R minus A whole square minus 1 divided by R plus A whole square into what? P cap. 1 divided by R minus A whole square, P cap is common. Now you have to solve this term, whatever the inside the bracket, we'll solve this one. So what you are going to get? Q divided by 4 pi epsilon naught as it is. Now take the LCM and solve. If we solve this, actually this becomes R square minus A square. R square minus A square whole square. Denominator. Numerator become 4AR. 4AR into what? P cap. 4AR P cap. Okay, how we got this one? If you want, I'll explain these terms here. Actually, what is a r minus a whole square, correct? R minus a whole square into r plus a whole square. This I can split and write r minus a into r minus a into r plus a into r plus a. We can write that one. Okay, combine these two and combine these two. First and last two combine. R minus a, r plus a becomes what? R square minus a square, correct? And this also gives same thing, so becomes a square, that only written denominator. And this term will go to the numerator here, r plus a whole square minus r minus a whole square square this one and solve this one. So what value remains? 4ar remains. If you want like this, you can try. Okay. So next, so E vector equal to this, I can split and I can write that one now. So 1 by 4 pi epsilon naught constant as it is. This 4 I'll write as 2 into 2a and this q I'll write together into p cap. Extra one r is there. I can write that one. Divided by r square minus a square whole square. Now what is that 2a q p cap? That is called dipole moment. So dipole moment P vector equal to 2aq p cap. Therefore I can write here now E vector equal to 1 by 4 pi epsilon naught 2 into I will highlight that term here. This much term becomes what? P vector into R divided by R square minus A square whole square is the equation. R square minus A square is the equation. Okay. So this is the equation for electric field due to dipole along its axial line. Okay, that means direction of the electric field and direction of dipole moment both are same here. Direction of electric field and direction of dipole moment both are same. Okay, let's show here now. Okay. So resultant direction comes where? Resultant direction comes here. Direction of the dipole moment and electric field is same. So resultant direction comes this way. Okay, completely go to the derivation once again. Derive an expression for electric field due to electric dipole along its axis. Okay, so you have taken one dipole, positive and negative charges separated by a small distance, that is 2a. Let P be a point and a distance r along this dipole axis. Total distance is 2a, so here to become a. From center this negative becomes a. So positive charge to point P is r minus a, positive point P to negative charge is r plus a. So electric field at point P due to plus Q is 1 by 4 pi epsilon naught Q divided by R minus A whole square. Electric field due to positive charge and dipole moment both are same, so becomes a P cap. Next, electric field at P due to negative charges 1 by 4 pi epsilon naught Q divided by distance R plus A whole square. But negative charge electric field is where inward and dipole moment is opposite here, so become minus P cap. After direct to add this to vectorically, just write this one. Written here minus sign taken outside. Take the common outside Q divided by 4 pi epsilon naught. First here remains 1 divided by R minus A whole square. Second one 1 divided by R plus A whole square into P cap. LCM you take and solve, that becomes your 4AR divided by R square minus A square whole square into P cap. This 4AR we can add as 2 into 2. A and this Q is taken here, P cap and into R. Now 2AQ P cap is known as dipole moment. So P vector equal to 2AQ P cap, and electric field and dipole moment both are in the same direction here. So it's the equation. Now from here also multiple choice questions are possible. They can ask the equation, they can ask the direction or angle between electric field and dipole moment. What is the angle here? Theta is 0 degree. And they can ask for short dipole also. They can ask for short dipole, that also right here now. So next point I'll write here for short dipole. Note for reference, note if short dipole, if R is very large compared to A, the distance is very large compared to the A. The distance charge is very small. In that case, what we can write here? A square very closer to 0. And denominator what term is there? R is there. R minus, that is R square minus A square is there. Whole square. So what answer you are going to get? R square minus A square whole square is it? This comes how much? R square minus anyway. Whole square becomes how much? R to the power 4. So what am this formula then? E vector equal to 1 by 4 pi epsilon naught 2 P vector R divided by R to the power 4. So 1 R will get cancelled out here. So at the end what remains here? At the end we are going to get this one. E vector equal to 1 by 4 pi epsilon naught 2 P vector divided by R cube. 2P vector divided by R cube is the equation. This is for short dipole. This was short dipole. So electric field E is equal to 1 by 4 pi epsilon naught 2P vector divided by R cube. Now what is the angle between electric field and dipole moment? That angle how much we can write? That angle we can write as how much? Theta equal to 0. Angle between electric field and dipole moment, that is theta is 0. And this also is possible here. Electric field is inversely proportional to R cube. Electric field and distance are inverse proportional with the cube, R cube. So these are the different questions are possible here based on this electric dipole along the axial line. So I hope this derivation is clear here. Next I'll go for electric field due to dipole along the equatorial line. So I'll go next derivation of along equatorial line. So take the question. Derive an expression for electric field due to dipole at a point on an equatorial 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 line along equatorial line. We have derived expression for electric field due to dipole along which line? Equatorial line we should find. Here also electric field due to dipole only, but we should derive the expression along equatorial line. Now this question repeated 3 times in the final exam. Okay, we'll derive the equation now. So I hope you have taken the question. So start deriving the derivation now. So I'll take now two charges here, positive charge and negative charge separated by small distance. Okay, so I'll take one here positive charge and negative charge. So here comes a plus q and here comes a minus q. These two are separated by a distance how much 2a. Okay, the distance how much here 2a is the length of the dipole. Okay. These are charges separated by distance 2a. Somewhere here comes the midpoint here. What is equatorial line? A line passing through the midpoint and perpendicular. That is called as equatorial line. A line passing through the midpoint and perpendicular. That is called equatorial line. Okay. So let P be a point. I'll mark this point as P. What is this distance now? This distance I'll mark it as how much here? R. Distance from here to here, from this axis to the point. Okay, point P. Now, so this distance is 2a, here to become much here. So I'll join one more line here to here. That distance I'll take it as how much here? Pythagoras theorem we should apply. That distance will take it as root of r square plus a square. Similarly, this distance also will calculate same value. Use a scale and draw this one. This also same thing. Root of r square plus a square. Okay. Now I'll derive the derivation here. Now start writing. Okay. So I'll write here now electric field at P Q2 plus Q. What is that one? E is equal to, I write E plus Q equal to how much? 1 by 4 pi epsilon naught Q divided by what the distance here to here? The point P to the positive charge. That distance is root of r square plus a square whole square. So this becomes here. So E plus Q is equal to 1 by 4 pi epsilon naught Q divided by r square plus a square. Root will cancel. So what is the direction here? Positive charge. What is the direction? Positive charge, that is away from the charge, away from plus Q. So we'll write away from plus Q. So positive charge away from plus Q. Away from plus Q. Positive charge, it is away. Away from plus Q. Okay. So what is the direction now here? So I extend this line. Same line I am going to extend here. So this is the direction of electric field. You take the scale and do that one. So this become now E plus Q vector. Same line, same straight line you should extend. Same straight line you should extend that here. Okay. Next, similar will write electric field at P. I'll write now short form. Electric field at P due to minus Q is. So the formula now. Now I'll write E minus Q vector. I'm sorry, I cannot write vector here. E minus Q is equal to 1 by 4 pi epsilon naught. Negative cannot put, only magnitude. Q divided by distance from here to here. Once again, same name will get point P only. From here to point P to minus Q becomes how much? Same distance, root of r square minus a square whole square. So becomes r square plus a square whole square. Root will get cancelled. Now what direction here? Negative charge, what is the direction of electric field? Towards minus Q. Electric field due to negative charges towards the charge. So become like this. Same length will draw. It's a straight line. Okay. Same line. I'll mark the direction of the electric field also. So you make one straight line by using scale. Okay. Now this length and this length should be same. This is E minus Q vector. E minus Q vector. Okay. Here I can put vector symbols, but here I cannot put the vector symbols here. Okay. So I hope this much is clear now. Electric field due to positive charge and electric field negative charges we got here, and directions also mentioned. Now you may observe that this electric field neither in the x-axis nor in the y-axis. Then what you have to do? We should resolve these two. You are resolve. So I'll take, this is my x-axis reference I'll take, and this is my y-axis. I'll extend that one. Okay. Now this, I'll bring one angle here, theta. So here I'll write theta. So here also become as theta. Because these two sides are equal, here also become theta. So this also angle becomes here theta. If we resolve this one, E plus Q vector, that becomes how much now? E plus Q, this side become cos theta. Because this vector makes angle theta here, so this side becomes cos theta. And here becomes what? E plus Q sin theta. So E minus Q we resolve here. So it becomes here E minus Q cos theta. This is in the fourth quadrant. Angle is here. So become E minus Q cos theta. And this becomes E minus Q sin theta. Refer the diagram properly. Now you can observe both the angles are same. Theta itself. Angles are same. And E plus Q value and E minus Q value observe. Once again they are also same. The magnitudes are same. Only directions are different. Now what you can observe here, E plus Q sin theta and E minus Q sin theta both are equal in magnitude and opposite direction. What will happen? They will get cancelled out. So we can write here now, resolve, we'll write that point first, resolve E minus Q vector and E plus Q vector, E plus Q and E minus Q into its rectangular components. Okay, we already resolved that here. Now observe the values of E plus Q, E minus Q, and this one E plus Q sin theta and E minus Q sin theta. E plus Q and E minus Q values are same. Once again angles are same. What happens? These vertical components will get cancelled out. Then right here vertical components cancel out. Vertical components cancel out. Then what happens to horizontal components? Horizontal components add up. Horizontal components add up. Therefore, resultant electric field. So what is the resultant electric field then? Resultant electric field come this direction. You can see that. Okay. Now I'll speak about electric dipole moment. What direction of electric dipole moment? Negative charge or positive charges. So this is the direction of the electric dipole moment. From where to where? From negative charge to the positive charge. Minus Q to plus Q is the direction of the electric dipole moment. Now this direction of the electric field and this direction of dipole moment both are opposite, and these two components are in the same direction. We'll add these two. E plus Q cos theta, E minus Q cos will add. So I write here vector form. So becomes what now? E plus Q cos theta plus E minus Q cos theta. Okay. Left hand side I wrote vector symbol. So right hand side also I should bring vector. So this is the direction here and dipole moment here. So both are opposite. So I'll put here minus P cap. Meaning this electric field and dipole moment both are in the opposite direction. So written as minus P cap. Okay. Now you can observe that minus I'll put outside. E plus Q and E minus Q values are same. Any one you take and continue that one. I'll take plus Q or minus Q. Values will be same. E plus Q cos theta into P cap. E plus Q cos theta into P cap is the equation. Okay. So therefore, next we'll find what is this cos theta. We'll find that value. What is the value of cos theta? I'll do that here. Cos theta. What is the formula of cos theta? Cos theta is adjacent side divided by the hypotenuse. So theta is here. Which is the adjacent side? Distance from here to here. That distance how much here to here? A. From here to here distance how much A? The complete length is 2A. So cos theta becomes our adjacent side A divided by hypotenuse with the root here. So that I'll write here. Cos theta is A divided by root of R square plus A square. Root means power is how much? Power is half. So R square plus A square whose power is half. Now we'll find this E vector. We'll continue the same steps. Minus 2 into E plus Q or E minus Q value is how much? Here both values are same. 1 by 4 pi epsilon naught Q divided by R square plus A square. We'll calculate, substitute, calculate those values. Substitute 1 by 4 pi epsilon naught Q divided by R square plus A square into cos theta. Cos theta value how much here? A divided by R square plus A square to the power of into what? P cap. Cos theta value A divided by R square plus A square, power is half. Okay. Now I'll combine everything here. So E vector become minus 1 by 4 pi epsilon naught 2AQ P cap divided by R square plus A square, power is how much here? 3 by 2. Minus 1 by 4 pi epsilon naught 2AQ P cap divided by R square plus A square. This power is how much here? 1. This power is 1. Here power is half. So 1 plus half becomes how much? 3 by 2. Now what is this numerator term? 2AQ P cap. That is dipole moment. So what is dipole moment? Dipole moment is P vector equal to 2AQ P cap. 2AQ P cap. So E vector equal to minus 1 by 4 pi epsilon naught P vector divided by R square plus A square to the power 3 by 2 is the equation. R square plus A square to the power 3 by 2. R square plus A square to the power 3 by 2. So minus 1 by 4 pi epsilon naught P vector divided by R square plus A square to the power 3 by 2. Now later we can try it for short dipole. That we'll do later. Now quickly we'll go to the derivation once again. So derive an expression for electric field due to dipole at a point on an equatorial line. Okay. So we have taken one dipole, positive charge here, negative charge here, separate distance 2a. So this is equatorial line. At point P, we want to calculate electric field. So what is equatorial line? Line passing the midpoint and perpendicular to the axial line. That is called as equatorial line. So P at a distance r from this one. So a distance from point P to the positive charge, the root of r square plus a square. And this distance becomes how much here? A. So when the point P to negative charge, the same thing, root of r square plus a square. And electric field due to positive charge is outward, negative charge is inward. So already know that one. So electric field at point P due to plus Q is 1 by 4 pi epsilon naught Q divided by distance root of r square plus a square whole square. So root will go. Just becomes 1 by 4 pi epsilon naught Q divided by r square plus a square. Direction is away from plus Q. Next, similar due to negative charge, same equation, but direction becomes what? Towards negative charge. Because charge is negative, so direction of the electric field is towards. Now these two vectors, neither in the x-axis nor in the y-axis, so the different direction. So we have to resolve these two. We have to resolve. Okay, we'll resolve into two components. The next statement you are right. Resolve E plus Q vector and E minus Q vector into its rectangular components. Now what will happen now? Vertical components will get cancelled out because they are equal in magnitude opposite direction. So theta and theta we brought here. Resolve this theta, E plus Q consider here, E plus Q sin theta. The E minus Q consider here, E minus Q sin theta. And horizontal component add up, so they will result in electric field. Add both. A minus P cap comes because electric field comes in this direction. Dipole moment is from where to where? Minus Q to plus Q. Both are in opposite direction. Opposite direction. So what happens? Minus P cap is a notation. So add both. Minus E plus Q cos theta P cap. So cos theta is equal to A divided by root of R square plus A square. So A is root means power is half. So E vector equal to minus 2 1 by 4 pi epsilon naught Q divided by R square plus A square into cos theta A divided by R square plus A square power is half and P vector P cap. So 1 by 4 pi epsilon naught 2AQ P cap divided by R square plus A square power is 3 by 2. So dipole moment P vector equal to 2AQ P cap. Replace that one here. So equation become minus 1 by 4 pi epsilon naught P vector divided by R square plus A square power 3 by 2. Okay, next we can write one note for short dipole. Short dipole means what? R is very large compared to A. Then what happens here? A square very close to how much? 0. So R square plus A square to the power 3 by 2. This value becomes R square plus 0 to the power 3 by 2. So becomes here R cube. 2 will get cancelled out. So what the equation you are going to get here then? So becomes here E vector equal to 1 by 4 pi epsilon naught with a minus sign. P vector divided by denominator become just R cube. This is for short dipole. Now here you can see that here you got minus sign means electric field and dipole moment both are in the opposite direction. Electric field and dipole moment are in the opposite direction. So theta is 180 degrees. And this is so equatorial line and axial line and equatorial line ratio becomes how much? So just write here. So E axial for the short dipole, E axial divided by E equatorial, answer become how much here? 2 is to 1 or 2 by 1. One is negative, other one is positive. Axial is positive, equatorial is negative. Negative means the directions that indicates the direction. No other meaning. Positive means direction of the electric field and dipole means both are same. Negative means both are in the opposite directions. Okay, so I hope this one is clear here. So two more questions we are going to discuss from this chapter that are based on Gauss law. Okay, so next possible question. Question is random. State Gauss law. State Gauss law. Obtain an expression. Obtain an expression or derive an expression. Expression for electric field. Electric field due to an infinitely long straight uniformly charged wire. Uniformly charged wire. Okay, this is actually a question. First question is asked here, state Gauss law. You already know the statement. For revision purpose, just write that one statement. Okay. So what the Gauss law says? The total electric flux. The total electric flux. Flux through a closed surface. Through a closed surface. Closed surface in air. In air is equal to. In air is equal to 1 by epsilon naught times 1 by epsilon naught times 1 by epsilon naught times total the total electric charge the total electric charge within the surface. Total electric flux through a closed surface in air. Total electric flux through a closed surface in air is equal to 1 by epsilon naught times total electric charge within the surface. Total electric charge within the surface. Total electric flux through a closed surface in air is equal to 1 by epsilon naught times the total electric charge within the surface. Total electric charge within the surface. Clear. The total electric flux through a closed surface in air is equal to 1 by epsilon naught times total electric charge within the surface. That means total electric flux surface is equal to 1 by epsilon naught times whatever the charge present inside the surface that gives electric flux. And there is one more formula for electric flux during derivation we are going to discuss. Okay. Now question is asked to derive an expression for electric field due to uniformly charged straight infinitely long wire. Okay. So I'll take one wire here. Length is infinitely long. One thin wire I will take here. So I'll take one wire here whose length is infinitely long. Okay, so I'll take one wire whose length is very long. Okay. So I'll take one wire whose length is infinitely long. That's why I put a dotted line like this, meaning still is going to continue. Okay. Now it is positively charged. I'll mention the charge inside this by the difference so that you can see that properly. Positively charged I'll take. Okay. So I'll take one point P here. Somewhere here I'll take the point P. Somewhere here I'll take the point P. At a distance, how much here to here? That distance I'll take it as R. At this distance, I want to calculate electric field, and we know that electric field due to positive charge it is outward. So you are going to get like this. Now at a distance of R from the wire in all direction remains the same. If I join all these points, what direction you are going to get? What shape you are going to get? Cylindrical shape you are going to get here. At the same distance I am going to draw. Okay. Okay, this surface is known as Gaussian surface. So what are things are there? We'll just explain. This one's charge. This one is linear charge density. This wire. I'll use different color here. It becomes. This is linear charge density. This wire that is lambda, and length of the wire I'll take it as a small letter L from here to here. In the infinite long wire I selected only small region. That length I'll take it as a small letter L, that is called Gaussian surface actually. Next I'll represent this one as what to Gaussian surface. This is called Gaussian surface, which is imaginary. Okay. Now still I can discuss more points here. This is a cylinder actually, like the cylinder is there, correct? I'm not going to go in detail here, just briefly explain. Inside this wire is there. So electric field present only in the outer direction along the surface. And what happened this one here? This electric field and this electric field both will get cancelled out. I mean there is no flux through this region and this region. Only the curve region field lines are flowing. Therefore, you are going to calculate electric flux through that region only. Where a curved surface electric field lines, they will get cancelled out or there is no electric flux. Only the curve region there is an electric flux that we are going to calculate. Okay. So briefly, I am going to discuss this one. We are going to derive this one. First one comes linear charge density. Linear charge density. What is this linear charge density? That is lambda. That is equal to what? Q by L, or that is Q is equal to. We can write above only linear charge density. So I'll write here lambda equal to what? Q by L. Linear charge density lambda is equal to Q divided by L. Linear charge density charge divided by the length. So charge becomes now lambda into L. So charge present in this Gaussian surface is how much? Lambda into L. Okay. So next we'll calculate now electric flux through Gaussian surface. So in theory class already discussed why this flux will get cancelled out, because two reasons. Wire is straight and uniformly charged, infinite long. So how many charges are above, same charges will come down. So flux along the wire will get, the field along the wire will get cancelled out. Only curved surface will get. So phi E equal to formula is EA cos theta. Electric flux to a surface given by basic formula electric flux, this one EA cos the surface area. So cross section area not required and only curve region you have to take. Formula becomes 2 pi r into L. Theta value how much here? 0. That means electric field and area vector both are in the same direction. So E into 2 pi RL, equation number 1. Now from Gauss law, same electric flux you have to calculate. From Gauss law we'll calculate. So what is the formula? Phi E equal to 1 by epsilon naught times Q. It's a Gauss law. Now what is that Q term? So phi E equal to 1 by epsilon naught times Q we got here lambda into L. That we write here. Lambda into L, equation number how much here? 2. Lambda into L, equation number 2. So what happens? Next step, what you have to do now? Equate both the equations. 1 is equal to, equate both. 1 is equal to 2. So equation number 1 is what here? E into 2 pi r into L equal to 1 by epsilon naught times lambda into L. So what happens? L is going to get cancelled out. So you are going to get E is equal to 1 by 2 pi epsilon naught lambda divided by r is the equation. You can stop here. Still you want to continue, you can continue that one. Multiply by 2 divided by 2. So you get 1 divided by 4 pi epsilon naught 2 lambda divided by r is the formula. Or if you want to write in vector form, if you want to write in vector form, you can write E vector is equal to 1 by 4 pi epsilon naught 2 lambda divided by r into n cap or r cap. So what is that? N cap is a radial unit vector. N cap is a radial unit vector. Okay, this is the derivation. We can go through once again this entire derivation once again. State Gauss law, obtain an expression for electric field due to an infinitely long straight uniformly charged wire. So electric flux to a closed surface in air is equal to 1 by epsilon naught times total electric charge within the surface. Okay, that is a Gauss law. Now this one wire we have taken, infinite long wire. In that wire we have selected only length L. At a point P we want to calculate electric field here. At point P we want to calculate electric field. Okay. This point, what distance now from the wire to here is how much R. Positive charge electric field is outward. So anywhere you take at a distance of R from this wire, field remains same. If you join all the points, we are going to get one Gaussian surface and there is no electric flux through in this region or in this region. Only the curved surface outward there is a electric flux. So linear charge density lambda equal to how much here? Q by L. So Q is equal to lambda into L. Electric flux through Gaussian surface phi E equal to EA cos theta. So E into A 2 pi RL theta is 0. So phi E is E into 2 pi RL. Next from Gauss law, phi E is equal to 1 by epsilon naught times Q. Q is what? Lambda into L, equation number 2. Equate both. E into 2 pi RL equal 1 by epsilon naught times lambda into L. So L will get cancelled out. E becomes 1 by 2 pi epsilon naught lambda by R. So usual our constant is 1 by 4 pi epsilon naught. So to get that one, multiply by 2 and divide by 2, it become 1 by 4 pi epsilon naught 2 lambda by R. If you want to write in vector form, you can write E vector equal 1 by 4 pi epsilon naught 2 lambda by R into n cap. N cap is a radial unit vector. Okay, so next question we can discuss here. One more derivation we can discuss. electric field at a point outside uniformly charged spherical shell placed in vacuum. Same one you can derive now. So take the next question then. Derive an expression. Expression for electric field at a point outside the outside the uniformly charged spherical shell placed in vacuum using Gauss law. Where is your question? Based on Gauss law, is a Gauss law application actually. Okay. So we derive this one. Directs for electric field at a point outside uniformly charged spherical shell placed in vacuum using Gauss law. Along with this one, question comes state Gauss law, but I didn't write that one because I already wrote it once. Same thing can repeat again. Outside is asked here, we can calculate inside also. So what the question is asked, that will answer first. Electric field outside the spherical shell will calculate. Okay, so first I'll take one spherical shell here. I'll take one spherical shell, means hollow spherical shell, like football or volleyball type. I'll draw the diagram here. So this is the diagram. Now this diagram for us look like one ring type, but it's not ring or circle. It is a sphere, hollow sphere, spherical one. Okay. So this is uniformly charged. On this one, charge is present. Positively charge will take plus, plus, plus. Positively charged. So radius of this one, I take it as how much here? R. This is the center. Radius of this one, will take it as how much? R. R is the radius of this sphere. Center is O. So I want to calculate electric field at a point P. Somewhere here I want to calculate at this point P. At what distance? That distance is small letter r. And this charge was how much here? Q. On the surface, Q is the charge. Now at a distance r from the center of this spherical shell, electric field throughout remains same. So at the same distance will mark and join all the points. Okay, we'll mark this one at a distance of r here. Okay. Now this one's shape also sphere only. We can call this one as Gaussian surface. And this this sphere surface charge density. This one's surface charge density sigma. Sigma, but you are not using that term. Okay. Now this one is called as a Gaussian surface. This is known as Gaussian surface. which is imaginary. Okay. Just we can explain the terms here. R is radius of the spherical shell. Spherical shell, and Q is the charge on this spherical shell. Charge on this spherical shell. On this spherical shell. Next, electric flux to the Gaussian surface will calculate. Electric flux through the Gaussian surface. To the Gaussian surface. Electric flux to the Gaussian surface. What is the formula? Flux to the formula is phi E equal to EA cos theta. So phi E equal to E as it is. What is the area here? 4 pi small letter Gaussian surface radius is small letter r. Theta how much? 0. Electric field and area vector both are in the same direction. So E into 4 pi r square. Equation number 1. Next, from Gauss law. From Gauss law, what you can write? Phi E equal to 1 by epsilon naught times Q. Phi is 1 by epsilon naught times Q. We'll take this equation as 2. Equation number 2 is Q is already mentioned in the diagram, so no need to calculate once again. So Gauss law will keep as it is. So 1 by epsilon naught times Q. Now equate both. 1 is equal to 2. So E into 4 pi r square equal how much? 1 by epsilon naught times Q. So rearrange 1 by 4 pi epsilon naught Q divided by r square is the formula. 1 by 4 pi epsilon naught Q divided by r square is the formula. Now if you want to write in vector form, we can write that one. So that is E vector equal to 1 by 4 pi epsilon naught Q divided by r square into what here? N cap or r cap. R cap or N cap is a radial unit vector. Radial unit vector. R cap or N cap is a radial unit vector. Now whatever we derived here, there is an electric field inside the spherical shell. This only asks the question. So I'll write here side heading as electric field, I'm sorry, this is the outside. Outside the spherical shell we calculated. Now later we can calculate for inside also. Outside the shell. Electric field outside the shell we got. Now later we can calculate inside also, but inside already we know the answer. What is electric field inside the spherical shell? That is 0, because there is no charge present inside the spherical shell. So first we'll go through this one. We have taken one spherical shell. This is the spherical shell, the black color one, whose radius is capital letter R. On the charge present how much here? Q. I want to calculate electric field due to the spherical shell outside at a point P. Distance how much? Small letter r. At small letter r from the center of the spherical shell throughout electric field remains the same. Join all the points, we are going to get one more sphere. That surface is called as Gaussian surface. And what direction of that electric field? Electric field is outward like this, because that sphere is positively charged. Positive charge electric field always outward. Okay, so surface charge density of this one is sigma, and this is Gaussian surface. So what is the charge present inside this Gaussian surface? It is Q. So R is the radius of the spherical shell. Q is the charge on the spherical shell. Electric flux to the Gaussian surface phi E is EA cos theta. A become 4 pi r square theta is 0. So phi is E into 4 pi r square is the formula. That is equation 1. Next from Gauss law phi is 1 by epsilon naught times q. Now equate both 1 is equal to 2. So E become 1 by 4 pi epsilon naught q divided by r square is the equation. And you can write in vector form E vector equal to 1 by 4 pi epsilon naught q divided by r square into r cap. R cap is radial unit vector. Next, one more note point we can discuss the electric field inside the spherical shell. In this question, that is not asked, but still we are doing that one. If some anyway is asked, some of the supplementary exam that is asked, that is going to be a 1 mark question. Okay. So electric field inside the shell. Electric field inside the shell. Okay. So I'll take one sphere. Same sphere we'll take. Okay. So this is positively charged. Same sphere, but I drawn little bigger here. Positively charged. So what is the charge present on this one? Plus Q is the charge present on this one. So radius of this sphere is how much here? This is capital letter R. And we want to calculate electric field at this point. I want to calculate electric field at point P. At what distance here? That distance is small letter r. So join all the points here. The distance of r, field everywhere remains same. Now that is called as what? Gaussian surface. Now this one surface charge density sigma. And this dotted one is called Gaussian surface. Gaussian surface. Okay. So we'll calculate now electric flux through Gaussian surface. Electric flux through Gaussian surface. Formula same as earlier one. Phi E equal to EA cos theta. Theta is 0 here. Phi E equal to E as it is. Area is how much? 4 pi r square. Theta 0. So phi E equal to E into 4 pi r square is the formula. Equation 1. Same as earlier one. Next from Gauss law. So we'll get phi E equal to 1 by epsilon naught times Q. Phi is 1 by epsilon naught times Q. So phi E is equal to 1 by epsilon naught times Q value is how much? 0. So answer becomes here 0. Why Q is 0? Because there is no charge present inside this sphere. There is no charge present inside this sphere. Therefore flux becomes 0. No charge present inside this sphere. Inside this sphere there is no charge present. Charges remains only on the surface. Therefore charge present in Gaussian surface is 0 or inside the spherical shell is 0. Now equate 1 is equal to 0, that means E is equal to 0. From 1 and 2 we can say the electric field inside the spherical shell is 0. So what is the reason for that one? Since there is no charge present inside the spherical shell, electric flux is 0. Electric field inside the spherical shell, electric flux through Gaussian surface. Phi is E into 4 pi r square cos 0. So phi is E into 4 pi r square. So from Gauss law, phi is 1 by epsilon naught times q. Q value 0. There is no charge present inside the spherical shell. Therefore, answer is 0. So this is outside the spherical shell we did, and this derivation inside. Actually, derivation is not important here. Same steps I copied here, whatever we did earlier. And in the place of Gauss law, Q value written as what? 0. That means there is no electric charge present inside the spherical shell. Therefore, flux becomes 0. That means electric field also 0 inside the spherical shell. Okay, so I hope this one is clear. Now we can go to the next concept. So I'll go to next question now. Second, next chapter we'll see. So first chapter, important derivations completed. 4 important derivations completed. So second chapter, I'll select only some 3 marks related questions. I select and discuss now. So next question was second chapter, important 3 mark question. Derive the relation between, important question this one. Derive the relation between electric field and electric potential. Important question. Many times this question got repeated. Derive the relation between electric field and electric potential. This is a question. Many times this question got repeated. Important 3 mark question. And very simple to derive this one. Okay. So we take now two surfaces, equipotential surfaces. Now first point, what is the meaning of equipotential surface? The potential on each point remains the same. Then that surface is known as equipotential surface. Potential on each point remains same, then that surface is known as equipotential surface. Point number one. Second one point is work done to move a charge on the equipotential surface is zero. Work done to move a charge on the equipotential surface is zero. And electric field is always perpendicular to the equipotential surface. And two equivalent surfaces never intersect. These are the characteristics or properties of equipotential surfaces. Okay, we'll start our derivation now. So I take now two equipotential surfaces. So I take now two equipotential surfaces. One already we taken, so one more will take. Two equipotential surfaces are taken here. They kept a parallel, one above this one, like in a room floor and the ceiling, like that. Two different levels. Okay. So these are the two surfaces. And what direction of the electric field here? So the direction of the electric field. Straight, perpendicular to the sheet. The direction of the electric field. Is the electric field. And this surface here is A, and this surface I call it as B. Here is V, and this one is how much? V minus dV. Now we want to move 1 coulomb of charge from surface B to surface A by distance how much? dl. That is gap between these two plates or sheets how much here? dl. Okay, we derive this one now. So that means I have two surfaces A and B, both are equipotential surfaces. Potential on surface B is V minus dV and potential on surface A is V. A is V and B is V minus dV. Next I'll write here force experienced by force experienced by a charge Q. Charge Q equal to 1 coulomb is. So what the force experienced by this 1 coulomb of charge, that is F is equal to Q into E. That means Q is 1 already mentioned, so become F is equal to how much E. Okay. Now work done. What is the work done here? Work done to move 1 coulomb of charge from where to where? B to A. Work done, that is F is equal to W is equal to F into DL into how much? Cos theta. The basic formula work done. So F is equal to what here? D E itself, and DL distance DL here, or dx we used to write here DL, and theta value how much here? 180 degree. Why 180 degree here? Because electric field acting upward, displacement is downward here. So angle becomes here 180 degrees. Okay. So cos 180 value how much? -1. So E into DL, equation of 1. Next one. Work done also equal to what here? Work done W is equal to final potential A minus initial potential B multiplied by charge. So W equal to final potential, what is that? V, minus initial potential, what is that? V minus dV into charge, how much you are going to move? 1 coulomb. So minus or minus, V minus V cancel, minus or minus become plus dV, equation number 2. So 1 is equal to 2, equate both the equation, 1 equal to, so we'll get E into DL equal to how much? dV. So E is equal to minus dV by DL is the equation. E is equal to minus dV by DL is the equation that gives the relation between electric field and electric potential. E is equal to minus dV by DL. This gives relation between electric field and electric potential. Okay. So we'll go through once again this equation. 3-mark question this one. Derive the relation between electric field and electric potential. So we'll take now your two equipotential surfaces A and B. They are kept parallel to each other. The gap between these two is how much? dl. Electric field is perpendicular to the equipotential surfaces. Potential on surface A is V. Potential on surface B is V minus dV. That means in the direction of the field, potential decreases. In the direction of the field, potential decreases. So gap between these two plates or surfaces is dl. So we'll take 1 coulomb of charge. That charge we should move from surface B to surface A. For the two formulas are there. One formula from the potential chapter, I mean this chapter. One is the basic formula of work done. So first 1 coulomb of charge is on the surface, anyone actually is present on B. So what is the force experienced by that charge? The formula F is equal to Q into E. Q is 1 coulomb, so become F is equal to E. Then force and electric both are same here. Now what is the work done? W is equal to F dl cos theta. So F becomes here distance dl only, or displacement dl. Theta is how much here? 180, because electric field upward here. So the electric field and displacement downward. So 180 degree. Cos 180 is how much here? -1. So becomes W is equal to minus C into dl. Next work done. W is equal to VA minus VB into Q. So W is equal to VA minus V minus dV into 1. So W is equal to dV. So 1 and 2 you equate. So minus E dl equal to dV, or E is equal to minus dV by dl is the equation. Okay. So next we'll continue. We'll go to the next question now. Derive an expression for next derivation. This is small 3-mark question. This also 3 marks. So derive an expression for electric potential energy. derive an expression for an electric potential energy. Electric potential energy of a system of two point charges point charges in the absence of electric field. In the absence of external electric field. External electric in the absence of external electric field. Okay, derive an expression for electric potential energy of a system of 2 point charges in the absence of external electric field. This was important 3 mark question. So I'm selecting some important questions and those questions I'm discussing here. Okay. So I'll take now two charges Q1 and Q2. Assume that these two charges Q1 and Q2 both are present at infinity. So I want to bring the charge Q1 from infinity to one point here. I'll take that point A. So I want to bring the charge Q1 from infinity to point A. So what is the work done to bring the charge Q1 from infinity to point A? So we'll write that one here. The work done to move Q1 from infinity to point A is amount of work done to move Q1 from infinity to point A is W1. That work done becomes how much here? 0. Now why work done becomes 0 here? Because there is no external field is present, although other charges are present. In the free space, we are going to move the first charge from infinity to point A. That no work is required, therefore work done becomes how much? 0. Because there is no other charge present and there is no other field present. So work done to move the first charge is 0. Now we want to bring the second charge. Now work done to bring the work done to move Q2 from infinity to point B. From infinity to point B is, that is W2 equal to what you can add potential at B multiplied by charge. Okay, what is the meaning of this one? So I want to bring the charge to this point. I want to bring the charge, which one? Q2. Now what is the distance between these two? That distance I'll write as R12. Or just you can write R also, no problem. So VB is the potential at B due to which charge Q1. So what is that value? 1 by 4 pi epsilon naught Q1 divided by distance R12 into what? Q2. 1 by 4 pi epsilon naught Q1 into Q2 divided by R12. What is that to VB? VB is 1 by 4 pi epsilon naught Q1 divided by R12. Next, therefore, the total work done. So whatever the work is done, the total work done is stored as the total work done is stored as electrostatic potential energy. Now this total work done is stored as electrostatic potential energy. So we can write U equal to W1 plus W2. That is U is W1 anyway 0. W2 is 1 by 4 pi epsilon naught Q1 Q2 divided by R12 is the equation. Therefore, total work done is stored as electrostatic potential energy. So U is equal to W1 plus W2. W1 anyway 0. W2 is 1 by 4 pi epsilon naught Q1 Q2 by R12. We can go through once again this one now. Derive an expression for electric potential energy or electrostatic potential energy of a system of 2 point charges in the absence of external electric field. So initially Q1 and Q2 both are present at infinity. So we want to bring the Q1 and Q2 from infinity to point A. To bring the first charge Q1 or Q1 or anything, but we have taken Q1. Infinity to point A, then no work is required. In that case, work done is 0. Because there is no field is present. Now I want to bring the second charge Q2 from infinity to point B. Now this Q2 has to do the work against the field of Q1. Q2 has to do the work against the field of Q1. Therefore, the work done formula will become that time potential at B multiplied by charge Q2. So what is the potential at B? Potential at B due to only one charge is present earlier. What was the charge Q1? So 1 by 4 pi epsilon naught Q1 divided by R12 into Q2. So what is that VB value? 1 by 4 pi epsilon naught Q1 divided by R12. Therefore, total work done is stored as electrostatic potential energy. Therefore, this total work done is stored as electrostatic potential energy. This total work done is stored as electrostatic potential energy. Therefore, we can write U is equal to W1 plus W2. So, U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. This is the total work done which is stored as electrostatic potential energy. So I hope this much is clear here. So in this session we discussed almost 4, 5, 6 derivation we discussed here. In the first starting four maybe could be 5 mark questions, and these two we discussed last two could be 3 mark possible questions. Then other questions are possible here. What are the properties of charges? Coulomb's law. Those could be Coulomb's law, state and explain, write the Coulomb's vector form. These are the other possible questions in this part. So we can go through that one. At the end, we are going to discuss other questions that one. Properties of electric charges, properties of electric field lines. Those are also important 3 marks or 2 mark questions, possible questions. All those things we are going to discuss in our later classes. So I hope this much is clear whatever discussed till now. In the next class we'll discuss some other questions maybe from current electricity and other chapters we are going to discuss. Okay, stop here now. Thank you.